Rookie Club left Praha.
Mm-hmm.
I'm afraid with no one here. The owner. Okay.
Yeah, it's a lost one.
So we still have 2 minutes, so.
Uh-huh.
Okay, it's. I think those are
Sicuro non la vuoi? Se le salvano.
Another one is in D207 and D206. Okay, in the basement. Yeah. Oh, okay, yeah.
Yeah. Well, you have still 1 minute.
20 seconds.
It will work too well.
So maybe just go to the beginning.
Yes, it should work. Red button for later.
This one. Should be okay.
Okay, let's start another talk. The topic of this talk is HPC VoD transcoding on Openshift. This talk describes setup of for a publishing subscribe application, deployment model, usage of Gluster for persistent volumes, and challenges for such non-standard scenario. Presented by Federico Neibolo and Alessandro Arciello. Sorry.
Quite good.
Hi, everyone. This will be a talk quite after the chorus because it is not a developer talk. It is the transposition of a demonstration we run to a customer for a real use case of implementation of Openshift and Gluster storage. So I will ask you to leave for a while the hat of developer and think about the implementation of Gluster or Openshift from an enterprise perspective, which is quite challenging on the social part, mostly on the social part. So the agenda is quite simple because we analyze the 5 Ws, who, where, what we did, and when, and why we did it, as an enterprise customer experience. The first thing, the first W is who. Here's Alessandro.
Yeah, I'm a platform consultant. I'm actually switching to solution architect team. I basically work on configuration management at a customer side with, for example, Puppet, Foreman, Ansible technologies, and now I'm focusing on OpenShift, OpenStack, CloudForms, and so on. So basically with Federico, we are at customer side, letting work also configuring our technologies for customer purposes.
Yeah, and I'm an IT architect for that, and I'm working on. I've been working for distributed calculus at CERN and INFN, and now I'm working on OpenShift, OpenStack, and Gluster architectures. Where this project was built, it was built in one of in the Italian branch of one of the largest European broadcasters, which has about 21 million subscribers, and is expanding its online streaming and on-demand market with 10 million connected customers. So it was quite a huge architecture. Just to say, to look at which kind of data we are running through. This is the Gluster storage console, and for example, they have that sort of media content on Gluster, which is quite a huge size. So, for example, if you think about issues that can arise that can rise on Gluster, and you have a failure on some of the bricks, and you're moving something like happened a couple of months ago. You have to move. You have to recover after a failure 40 terabyte of storage. Assuming the hypothetical 10 gigabit network, it will take about 9 hours to move the data from one place to another. So it is, and you cannot use, of course, the 10 gigabit at all, because the environment is on production itself.
And in the meantime, the customer is complaining about that.
Yeah. Well, that's a side effect of working on that data. So this is the target size. But what we are talking about in this talk is about an Openshift application which is used for customer encoding workflow. Summarizing that application in a few lines, as I reported in the slide. The broadcasting content coming from broadcasting signal requires encoding activities to encode the content for all the different devices and size and frame rate in order to be dispatched to the customers. And this is an application developed by external system integrator. So the integration of Openshift in that environment, as you will see briefly, was not so simple. The workflow itself for encoding resembles a traditional job scheduler, so that there is we will see in the next slides, there's a dispatcher that takes segments, which are media content, from the broadcasting signal and transform it and encoded it with standard FFmpeg or similar programs. So the job scheduler is something like a traditional master agent architecture. Maybe some of you work with some of those technologies. Those are the technologies I've been working with in the high energy physics calculus, and those are the standard schedulers used in the last years. For example, Moab, Torque, which was formerly known as OpenPBS, which was an open source fork from PBS, or LSF if you use the IBM commercial product, or HD Condor if you use the one developed by the California University. So this is a traditional job scheduler software installed on single machine, where there's the concept of a master, and the concept is that the job is run by a small portion of the application, which is run on an agent. The agent waits for commands from the master, execute the jobs, which in our case is an encoding activity, and then returns the exit code back to the master. This is another graph showing you, well, you can't see the number, but this is a graph of taken from the Kibana interface of the encoding job running per hour. Each segment is a media content that has to be transcoded. And as you can see, the lines are quite similar in the input and in the output. The jobs are quite unpredictable because they're coming from the broadcasting signal, so we have no control on the sort of jobs that are coming and the rate. The overall workflow, summarized in a graph, is that broadcasting publishes a content signal acquired by a traditional graphic card. Then there's a legacy Microsoft app, because the driver for this card is it exists only for Microsoft, which is called the WFM, which realizes a streaming segment, which is an MP4, usually an MP4 content. Then this content is transferred to the hyper dispatcher, which is a legacy Java application, which was out of the scope of our port into OpenShift, and this was one of the challenges we have to cope with because we cannot move this part of the application itself. Usually, when you work in OpenShift, you're putting all or most of the workflow inside OpenShift. This was not the case, and we'll see soon how we did it. That the dispatcher split the encoding jobs, put the content on storage, and send it to the hyper agent, which encoded the segment, and most importantly is profile-based, so that there's a JSON which load the profiles for the frame rate and the dimension and all the other parameters that for the encoding. So we had some challenges to work on because the dispatcher was not in scope of the porting of this application. We have to first demonstrate to the broadcaster that OpenShift scale better than traditional VMs or traditional physical hardware. And we have to work with legacy physical nodes still working, and they are working still now because we have to work in parallel. We could not port the whole application to OpenShift. And on the other side, the advantages of this, the factor that simplified this application, this porting was that the node agent is quite simple. It's the Node.js application which publishes a REST API. And that the performance improvements were immediately tangible. So as soon as we deploy the first containers or the first pods, the performance increase was of an order of magnitude with respect to the traditional VMs. So this is just another slide focusing on the workflow just for the dispatcher. I think we can skip it. Okay, and now we have the architecture. We have to work in order to have a legacy application running within OpenShift and communicating both with single pods and with external entities like VMs.
Yeah, as you can see, we have a list of OpenShift nodes. Basically, all the nodes you see on this slide can be scheduled by OpenShift for running containers. The last one is the one containing the broker that actually is the legacy application. And this node is part of the OpenShift cluster, so it can actually access to OpenShift network and run the legacy application. With this trick, the legacy application can contact the internal container that actually, when loads up, contact back the broker, and broker itself will schedule new encoding on the registered client.
Yeah, the main reason is that in a publisher-subscribe architecture, the dispatcher has to contact every single pod as itself, and usually in OpenShift you mask the pod under a router or a load balancer or something else. While in a publisher dispatcher activity, you cannot rely on this, and the dispatcher has to contact every single pod, asking for idleness, asking for job status, etc. So it has to be part of the network of the agents themselves, and at the same time, part of the other network for the traditional VMs. This is another representation of the nodes in our environment. So we have seven Apollo nodes with tons of gigabyte of RAMs. There's a graph in a successive slide.
Another important thing is actually the customer agreed to use physical nodes to unlock the real power for the encoding jobs. So unlike the standard way of putting OpenShift over another virtualized infrastructure, in this case, customer wanted to run it on bare metal.
Yep. Then we have a simple, this is mostly customer based. We have to explain to the operation team how to work with Openshift, which usually goes on the other way as a developer usually works, because on Openshift you usually run from build configs, then you build images on top of that, and you on top of it, and then you can see at the end the final pods for the operation team, which usually is not involved into the build part, into the deployment part, but want just to see the running environment and see the logs and access to the traditional shells. They have to work on the other way around. So we started with them from the single pods where they can log in with OC remote shell. They could see the log with OC logs, and then we explained later that they can run a deployment, which represents all the pods running, and they can scale the deployment, adding pods at will. Okay, and then as a successive step, we explained them that these pods, this deployment, are run on image streams, which are provided with the agent software and the standard Node.js framework with all the libraries included. And then at the end, we explain them how to build this image stream, this image and the image stream related, running from the source code coming from the developer. So we have to treat the topics the other way around. We have the encoder agent deployment with the memory defined by system integrator. This was another success of Openshift, because we were able to demonstrate that they're oversizing their requirements for the memory needed, and they can do the manual scaling, adding on agent variables. And you can see again that there are mainly those are the most important environment variables, because the single pod has to announce itself to the dispatcher when it starts, so that the dispatcher now knows that there's one more pod and can schedule jobs on it. And this announcement is done on the agent dispatch URL. And then there's the profile Git, from which the profile JSON is loaded, so that the developer can modify the profile, the encoding, the frame rate, etc. And this is loaded at when the pod starts. Then we have the image stream coming from Node.js application with the hyperagent Git code. We deployed Git on top of Openshift, which is quite common. And then there's a build and how we run the build with a standard source to image workflow. This is another of the 5 Ws. So when we did it, we were able to run the whole process in just a little more than a month, which is a quite short time frame for an enterprise and for a project like that, because if you think of all the media contents that have to be streamed and the constraint for a production environment, and then we are constantly upgrading the environment, managing it, and the next step, for example, would be to put the dispatcher inside Openshift itself, which was a thing we couldn't do at the first time because of the constraint for the system integrator, and on the fact that the did not exist concept like pet set or daemon set in order to have a single instance of a pod running. Or another thing we missed, for example, was the egress router in order for the dispatcher to contact from the same source IP address the agents which are not inside OpenShift. This is a summary of why we did it, and we see that now we have OpenShift with a lot of resources available. And the Hyper Agent is working. They reduced the development cycle. If you think that previously they have to dispatch a single VM on the month, and this action lasts at least 1 day or 2. Now they can just scale the pods quite easily. We augmented the physical hardware density, and so they're running their pods, more pods than VMs. And then they also avoided technology lock-in in management, because now with environment variables, the customer can modify profile by himself, while before it was bound to the system integrator to modify those values. The project involved also Gluster, as I told you. And for example, this is an extract of the export. Gluster as a storage was an external project already in place. And here you can see that. Yeah, well, it's the last line. In this case, Gluster is exported as an external endpoint, and all the agents can write the media content directly on the Gluster FS on the Gluster FS cluster, so that the content is available to be presented by external origin server, which are mostly Nginx web servers. So thank you.
Any questions?
Yeah.
What do you use to build the images that are running then in the OpenShift nodes?
Sorry? When or?
What do you use to, which tools do you use to, which tool chain do you use to build the images, the distribution images that are run in the OpenShift node?
Yeah, okay. We run just the production building of the image with standard OC build config, as you saw in somewhere like
with the S2I.
Yeah,
S2I.
it is an STUI S2I source. We take the code from the system integrator, and we provided the Node.js version, which they required with all the libraries included.
We also deployed a Git server on OpenShift itself, GOX. For
we took
system
occasion.
integrator.
We took the occasion for them to deploy also an internal Git, which I just closed down because I clicked on. I don't have reopen this one. Because remember that the system integrator is providing us obfuscated code, which of course they do not want to show us all the internals of the application. So we have an already parsed artifact to be deployed on the image itself, and so we deployed that on Git and provide the image stream Node.js, which is version 6.2, with which the system integrator required, and the build config is run through OpenShift itself from the UI or from command line.
So you said the performance increased by an order of magnitude?
Yeah, more or less. We're still trying to collect data correctly. because we have a Kibana, we have an Elasticsearch, environment, which is an external one managed by another team, and they're not providing correctly all the data to us. But the customer told us that the project could continue because they saw a huge improvement in their performance. But we still do not have physical data to provide you.
Do you know and then the other comment was around augmenting their hardware by having more density. Do you know how much more density you ended up with?
Yeah, because for example, you see that now we are running 84 pods, which was a requirement by the system integrator, and they had less than 84 VMs before starting. So we translated the physical hardware and we replaced that from VMware. We uninstalled it, we formatted it, and put that into OpenShift.
So how many did they have before? They have 84 now. How many did they have?
Yeah, they have more. They have the half of virtual machines. But now, but to answer you, we just saw that the memory they require is quite huge for the task. So now we can downsize the single pods and increase the size, the number of them, which was not possible with standard VMs.
Okay, thank you very much.
Okay, thank you.
And as well, do not forget to post your feedback and rating of this talk. And who would like to sign up for tomorrow lighting talks, please do that at the white table right behind this wall.
Sì? No, Italia.